Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions to the speaker using the live video wall feature. All questions from the audience will be taken during the Q&A session after the talk. The webinar is being recorded, and the recording will be made available on the ITU Journal Webinars series playlist on YouTube. We hope that you will enjoy the talk, and we encourage you to stay connected until the end for the Wisdom Corner. Live Life Lessons. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series of the ITU Journal of Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Digital Technologies. It is my pleasure to open our first webinar of the season, kindly hosted by the Eye for Good as part of the ITU Journal Discovery Series with Professor Raj Jain from Washington University. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons, so please stay in line. Our speaker agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm very pleased to introduce now Professor Ian Akilditz, Editor-in-Chief of the ITU Journal, founder and president of Truva from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He is Editor-in-Chief Emeritus of Impact Factor journals and highly cited at the top of the most prestigious international rankings. Ian is visiting distinguished professors in many universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So, Ian, the floor is yours for your opening remarks to introduce our speaker and moderate a Q&A session. Thank you.
Thank you, Alessia. Good morning, good afternoon, and good evening to our global audience. Greetings from Atlanta. It is my privilege to welcome you to the ITU Journal Future and Evolving Technologies webinar series, which will launch in 2022 as we kick off a new season with episode 1. Once again, we have curated an exceptional lineup of speakers for this season, and I'm thrilled to introduce our first presenter and my longtime friend, Professor Raj Jain. Before I do so, allow me to briefly introduce our journal. The ITU-J FET was established with the mission of bridging academia and industry, fostering collaboration, advancing cutting-edge research. The inaugural issue was published in December 2020. As an open access journal, we charge no fees to readers or authors, ensuring that high-quality research is accessible to all. Each submission undergoes a rigorous peer review process, and we strive to cover the most timely and impactful research at the intersection of academia and industry. The success of the journal is a result of a collaborative team effort. I would like to take a moment to acknowledge the invaluable contributions of our director, Suzu Ona-san, Chief of the Strategic Department, Fred Werner, Head of the Strategic Tech and Academia Division, Vijay Mauri, Alessia Magliarditi, Erika Campilongo, Maria Otero, and many others. Their dedication, hard work, and unwavering support have been instrumental in shaping the journal into what it is today. I encourage all of you to consider submitting your research papers to the journal. Additionally, if you have ideas for special issues on emerging or popular topics, please feel free to reach out. Now, it is my great honor to introduce our distinguished speaker for today, Professor Raj Jain. On behalf of the entire ITU JFAT team, I would like to extend our heartfelt gratitude to Professor Jain for accepting our invitation and sharing his insights with us. Raj is currently the Barbara J. and Jerome R. Cox. Jerome Cox was also a professor at Washington University. I think he passed away. I hope not, but anyhow, Raj is a professor of computer science and engineering at Washington University in St. Louis, a position he has held since 2005. Previously, he was co-founder and CTO of Nina Networks from 2000 to 2007. As I can recall, Raj can confirm that it was an optical networking company, and those are the super times for the startups. He was also professor of computer and information sciences at Ohio State University from 1994 and 2002, and a senior consulting engineer at DEC, Digital Equipment Corporation, and Littleton, Massachusetts from 1978 to 1994. That was the time that we met in the 80s, and DEC was also very successful those years. And they had this product called VAX 11780, medium-sized computers. And the best time also they had this DECnet that even is taught in the textbooks. And Raj also taught several courses at MIT from 1983 until 1987. So when went through his bio on our website, you could see there was nothing. I was just telling him that he's so humble he didn't put any of those achievements. So I have to mention those, and I apologize, but anyhow, Raj is a fellow of the IEEE in 1993, and also fellow of the ACM 1995, and AAAS 2012, and the Academy of Science in St. Louis 2018. He has many honors, including 2018 James Eads Award from Academy of Sciences in St. Louis, 2017 ACM SIGCOMM Lifetime Achievement Award, and 2015 Michelson Award from the Computer Measurement Group, and many more. He is author and editor of 12 books, including the famous performance evaluation book called Art of Computer Systems Performance Analysis, which received the 1991 Best Advanced How to Book Systems Award. And many universities are using that as a textbook. They still do. He holds 15 patents and authored or edited 13 books and 20 book chapters, over 110 journal and magazine papers, and more than 130 conference papers. His research is known in quantum computing, AI, and blockchain applied to cybersecurity. Recently, wireless technologies for IoT, 4G, and unmanned aircraft systems, and in the past as congestion control, traffic modeling, performance analysis, and error analysis in wired, optical networks, as well as wireless networks. His work is widely cited, with Google Scholar listing over 45,000 citations. He is the co-inventor of this very famous DECBit-NET scheme. DECBit was very famous in the 80s, which has been implemented in various forms in DECnet and also OSI, frame relay, and ATM networks. And later on, this idea was used as explicit congestion notification, ESCN bit. I used to teach that in ATM networks. I always mention his name also. He has delivered over 60 keynote addresses, served on editorial boards of numerous journals, and he had this distinguished lecturer for IEEE Communication Society and ACM. On a personal note, I mentioned before, I first met Raj in the 80s when he was with DEC, and we served together on many conference committees and standards meetings, particularly during the ATM forum, when he was advocating for his ECN ideas, as I mentioned to you before, hailed from these DECBit ideas for congestion control in ATM networks. I have been in this business since 50 years like him. Raj is an excellent role model for the younger generation, exemplifying hard work, dedication, integrity, and honesty. It's really true. And without further ado, please join me in welcoming Professor Rajan as he takes the stage to deliver what promises to be an engaging and insightful presentation. Raj.
Thank you, Ian, for the introduction. That's better. That's better than what I really am. But anyway, and thank you all to join this talk. I suppose everybody can see my screen, and actually, on every slide at the bottom there is a URL. If you get there somehow, then you will be able to find all these slides there, and I will.
We don't see the slides.
We don't see the screen.
Yeah, and I will actually let you download it also from this screen and at the end of the lecture, so you can get it right away. You don't have to worry about it. So let's move on.
We don't
to
see the
why-
screen now. Can you please reshare, Professor
Oh,
Jamil?
you don't see the screen? Okay, let me start. Share screen share. Can you see it now?
That's perfect.
Okay, so welcome to this lecture on quantum networking, issues, challenges, and opportunities. This is actually a motivational lecture for computer science people. Motivational in the sense that not many computer science people are involved in quantum right now. And I hope some of those are here in this audience, because the lecture actually has four parts. Why quantum? And that is basically the motivational part, is that why you should be thinking about quantum right now. And second part is what is quantum. Now, many of you who are already involved in quantum will find maybe what is quantum little bit boring, but please bear with me, because that is required for some of the people which I generally meet. They have no idea what quantum is. And then how to do quantum networking, that is the most of the lecture, and then standards activities, and then what are the challenges in doing quantum research. And so why quantum? Basically, throughout our life, we will have to change our field. I did my PhD thesis in memory management. That was the hot topic back in whenever I did my PhD. And I never worked on memory management afterwards, because I joined DEC, where I joined networking group. And so I became a networking person, first Ethernet, then fiber optics, and then on and on, moving on to whatever problem becomes important. And nowadays, if you don't change, then obviously you will find yourself out of job. So nowadays, the technology in the early days, it used to change every 10 years. Then every 5 years. Nowadays, they change every 3 years. So whatever you see today is hot, probably will last for another 2-3 years, and then it will go away. So you have to keep moving. And so we have to find where the world is today. And that's what I keep doing. Basically, we have to find out what is hot right now. And it turns out quantum is hot, as I will show you. And before I go to the next slide, if you have a company, or if you're part of a company, the company will go bankrupt if you don't change with the time. And so they adapt by necessity. It's the academics like me who just keep working on the same old thing forever. And so, I mean, I don't do that, but basically that is what many of my colleagues do. So I just want to show you that, to say that United Nations has declared 2025, which was the last year, the International Year of Quantum Science and Technology. Okay, so they are emphasizing that this is the place to go. Second way to find out what is hot is to go to Gartner. What is Gartner? Gartner is a company that does a big survey every year on every problem that the world is facing, every technology actually, and their reports cost several $1,000s, which all the big companies buy to find out where the technologies are. And this is their hype cycle for 2025. They do it every year, and they do it for different fields like computing and communication and so on and so forth. And as you can see, basically what happens is the graph starts, the technologies start at the bottom, and most of it is done in the universities. Okay, there is very little money to be made, and there is a lot of work to be done. So universities do it. Once the technology becomes ready, then it moves to startups. This is where the startups come in. There, with very little investment, you can make a lot of money. And then it comes to the top where they are bought up by the big companies, and then the technology actually takes a downturn a little bit, and then either it can die or it can continue. If it continues, then it goes to Asian countries where it is mostly manufacturing. And so we really have to move back. We have to keep moving back to the left. And those of you who are in academia, you have to be, trying to find out what is the extreme left. Those who are in the industry, find out here. Big companies are here. And so quantum is the right time. This is the right time to get into quantum. And here is a quantum computer on the left, and here is a regular computer on the right. This is ENIAC, the first digital computer. It was a 10-register computer, and this is also around the same very small number of qubits computer. Now, this whole room is one computer. Why this whole room? Because all of these cylinders are things that are cooling. They are the cooling units. And so it requires 0 degree Kelvin. So that is where most of the energy and the parts and everything goes in quantum is cooling. Now they have really condensed it. Now you don't need a big room like that. And this is one of the latest thing. This is Quantum 2 from IBM. Now these 3 racks, they're all coolers basically. They are being cooled, and there are things inside it which are basically using that. So this is a example of a quantum computer today. Tomorrow it will be on your desk, but I don't know when. So what I'm saying is that this is just starting. Now there is a lot of investment in quantum all over the world. So Asia Pacific region has $40 to $45 billion. China alone has 15 billion for technology, and most of it is actually 15 billion in quantum out of 138 billion for tech, and quantum also is included, right? A lot of work is being done in China, and of course a lot of work is being done in European Union, over $10 billion, and then US government has spent 5 to 6 billion. Now US government number looks small, but that is by design. In the United States, the inventions come not from the government, they come from the companies. So if you talk about IBM, Google, and Microsoft and all that, they probably have spent more than the government. So this is the case. Amazon, Cisco, they're all involved in this. So in terms of academics, they look at where the funding is, and there is a lot of funding in quantum because NIST, which is the National Institute of Science and Technology in the United States, NSF, National Science Foundation, Department of Energy, Department of Defense, NASA, NSA, National Security Agency, IARPA, which is basically Intelligent Advanced Research Project Agency, all are coordinated by National Quantum Coordination Office. So there is one office which basically coordinates all the activities in all these places. Every state is trying to get into quantum. State government, for example, Illinois, where Chicago is, has set up a quantum park in Chicago. And they have invited all the companies to set up something there so that the quantum technology can get there. And they're all looking forward to it. In Washington, D.C., there is a network already being set up. So a consortium of US government agencies, many of these agencies on the top, they are setting up a functional quantum network, and that will use existing fiber over metropolitan distances, and there are many other test beds. Okay? For example, DOE has a quantum garage, quiet and loud facilities. Quiet is basically with very little noise in the basement, and loud is with some noise. And then NSF has a National Quantum Nanofab. So all the agencies are working on some form of quantum thing. And the main interest in the industry in the quantum came because of this one result. Basically, Peter Shor in 1994 showed that the quantum computers can factorize numbers exponentially faster than legacy computers. You see, factorization is very important because all security methods that we use today are based upon RSA, which is based upon factorization. And we say that, well, RSA 2048, it will take 100 years for you to break it. But with quantum, if it was there, it will take very little. Right now, you cannot do that because it needs bigger quantum computer than what we have today. But they will be coming soon. So we have to get ready for that. And that is basically the reason people got into quantum, but now they found so many other applications. And if I get time, maybe I will add some more slides about the applications. But this is one reason for getting into the quantum. Everybody knows that that is why people are in the quantum. And about 10 years ago, NIST started working on how can we protect from this quantum threat. Quantum threat because if the quantum comes, then the current security will break. So they started developing post-quantum cryptography. And now the standards have been set up actually. The standards have been, the whole thing has been standardized, and now people can just start implementing. So if you are a carrier, if you are not using post-quantum, then I think you are going to be in trouble because the people who are hackers, they are just collecting the data. Even if it is encrypted, they are saying that let's collect it now, and when the quantum comes, we can decrypt it right away. So that is called harvest now, decrypt later attacks. Those are happening, but we don't know that because they haven't decrypted it yet. So it is better to just start encrypting so that it cannot be decrypted by quantum. Now, however, having said all this about post-quantum, this talk is not about post-quantum. Okay? I actually advertised for a position of postdoc in quantum several months ago. And then half of the applicants said they know quantum and all they knew was post-quantum. Post-quantum is not quantum. Post-quantum is traditional computing. How will you protect from quantum? Okay, it is mostly anti-quantum rather than pre. Now, what we are going to talk about in this lecture today is everything about quantum, not post-quantum. So with that, let's move on to what is quantum. Now, I know many of you know this, but please be basically patient with this because many other people may not know this, okay? And so this is a very introductory part, next 3-4 slides. First is, what is quantum? Quantum, the word quantum comes from quantization. Basically, when you take a analog signal and you digitize it, you have to decide what is the unit that you are going to digitize in. Like voice, we digitize it at 64 kilobits per second. So basically, that is one quantum, one unit. So quantum is the smallest discrete quantity. Now, what about the light? Is light analog or digital? And physicists have been fighting it for 200 years about that. So light is a wave, and it has a frequency, phase, and amplitude. That is one theory. Other says no, light is not continuous. It is a discrete packets of energy that can be absorbed and released, and that packet is called photon. So you cannot have half of a photon. You cannot have 1.5 photon. You cannot have 2.5 photon. It has to be 1, 2, 3, or 4 photons. So this is the quantum. Quantum is one unit of light that you cannot divide any further. And it doesn't have to be actually light, as I will show you in a minute, but basically photons are energy that can move electrons from one level to the next. Okay? Or if the electron moves to a higher energy levels, it absorbs the energy. And if it moves to the lower level, it emits the energy. But energy always comes in units of photons, units of quantum. So that is what the quantum is all about, right? Unit of quantum. Now, to show that whether it is a particle or a wave, a very famous experiment which is mentioned everywhere is called Young's double slit experiment. So he took a wave source, a light source, and had it pass through two holes. Now, if it is a two hole, then some frequency, some signal will go like this, and some other signal will go like the other one, and the total waveform would be like this. Okay, that is what will happen. However, this is not what we get. We get lines. We get one line, and then we get another line, and then we get another line. We get another lines, and the another lines. Why? Because it's also photons, and wherever the photons meet, there is a light, and whenever the photons oppose or whatever they do, there is no light. So you see these lines, and that clearly says that it is also a particle. Clearly, so basically, photons are both particles and waves. That has been established in physics now. Both theories are accepted. Now people are questioning whether electrons are particles or waves. So now we have been taught, when I was learning physics, I was told that electrons are particles which circle around the photons or the nucleus. But now people are saying, no, they are waves too. So everything in the world is both a wave and a particle. In fact, some physicists argue that you and me are also wave, but now that takes it too far probably, but that might be correct. Everything in the world is both wave and particle, but that is not this lecture is all about. This lecture is about these photons, and so let's move on with that. So quantum bits. Computing bit, when we have a computer, we say the bit is 0 or 1, right? Quantum bit actually is a vector. You cannot write with one number. You have to write two numbers. It's a vector, either 1, 0 or 0, 1, or in general, it doesn't have to be 0 or 1. It could be alpha and beta. These are quantum bits, and these alpha and beta both could be complex numbers. 1 plus 2i divided by I under the square root of 6, and so on and so forth. So this is what a qubit is like. It is much more complex than a bit. And if you have 2 bits, then you need 4 y1 vectors. Okay, this is a qubit, this is a qubit, and this is a qubit. So basically, if you have n bits, you have to represent it with 2 raised to n element vector. It's very difficult to write all this. So people said, why worry about this writing vector? Why can't we make a notation? So there is a notation that has been developed, which is called Dirac bracket notation, bracket notation. And bracket actually is the two parts of bra and ket. So basically, when you want to write down a row vector like this, you say this is a bra 0, and this is a bra 1. And it will become clear as to why this is bra 0 and this is bra 1. The difference is here, the 0 is second, here 1 is second. And ket is a vector which is a basically column vector, and this is a ket 0 and this is ket 1. Okay, and this is written with the other side of the angle vector. This is left angle bracket, this is right angle bracket. And if you have alpha, beta, it can be written as alpha times 1, 0 plus beta times 0, 1, or it can be written as alpha times 0, cat 0, and beta times cat 1. And so if you have 2 qubits, then that can be written as by 4 numbers, alpha times 0, 0, beta times 0, 1, gamma times this, and so on and so forth. So this is the thing that we will be writing, because these vectors become too difficult to write. Now the next question is, what are these numbers 0 and 1? So the next complication with quantum is that they are probabilistic. The qubits are probabilistic. And so the elements, these values which you have inside the vectors, they indicate the probability. So this one says the probability of this being 1, being 0 is 1, and probability of this being 1 is 1, right? Probability of 1 being this is 0. So this is basically alpha times 1, 0 and beta times 0, 1. Alpha times 0 plus beta times 1 means is that this qubit, which is 1 bit, has a probability of alpha square upon alpha square plus beta square. So these are the proportional. So the probability is proportional to alpha, and the probability is proportional to beta. So alpha square is upon alpha square plus beta square is the probability of being measured in the 0 state. If you measure it, it will come out with this probability as 0. On the other hand, it can also come out as 1 state with this other probability, which is just 1 minus that. So until it is measured, we don't know whether it is 0 or 1. And that's one thing which we have, this is very important to understand, is that this is like flipping a coin. If I am flipping a coin and I flip the coin and I asked you, is the coin head or tail? We don't know that, right? Nobody can say for sure whether it is head or tail until it lands. So, but until it lands, until that time, it is in both head or tail position. And so this is called superposition. So qubits are always in superposition. They have never landed. They just in this position where it is like a flipping coin. Okay. And so they are in both positions 0 and 1 until they are measured. Measured means they are stopped. And the problem is if you measure them, you have stopped them, and they lose the quantum property. And whatever you get 0 or 1. That's what it is. Now you have to flip another coin if you want, I mean, you have to create another qubit if you want to use that. So the qubits basically cannot be measured easily as 0 or 1. So that is one thing, superposition. Okay. Second thing is no cloning. You cannot keep a copy of a quantum state. So that flipped coin, if I asked you to make a copy of it, you can't make a copy, can you? And so if you have a qubit which has alpha proportional to alpha probability of being 0 and proportional to beta probability of being 1, if you measure it, you will get either 0 or 1, right? And so you will lose alpha and beta. So you cannot make a perfect copy of that. So since no backup copy can be made, qubit is permanently lost. So unlike the normal qubits, where normal bits, where you make a copy and send another one on the network and keep one in the memory forever, that doesn't work here, right? So if anyone if anyone on the way reads the qubit, the receiver will know because it is lost. So suppose I send 5 qubits to you, and somebody on the way reads one of them. If they read one, that is lost, and it will not make it to me. And then I will know that one of the bits was lost, and so there is somebody who is eavesdropping on it. So the quantum link is more secure than classical links to transfer highly secure information such as encryption keys. So if you want to send something very, very secure, you use quantum. And we will talk about that a lot because ITU is working a lot on QDN, quantum distribution, quantum key distribution, QKD, quantum key distribution. So that is one of the applications of quantum is key distribution. A third property of quantum that makes it very interesting is entanglement. Now, I generally introduce this to people. It's like two people, and I'm sure this happens to you, or you have noticed that if you have somebody that you love, when you are thinking about them positively, they are thinking about you positively. If you start thinking some negative, the negative thoughts they will be thinking too. Has it happened to you? I mean, it happens a lot, right? That is because those two people are entangled. And same thing for qubits. If two qubits are entangled, if you measure one, the other will stop. If one lands on head, the other will also land on head. So they are so much entangled that you can't really, they're not separable in some sense, right? So two qubits can be entangled. Their states are correlated. So basically, again, there is a probability here, and they have very high correlation, means very high probability of what I am saying, right? And that is what the entanglement is called, right? And if they're photons, their momentum, their spin, their polarization or position are correlated. So one of these things is what we are measuring, and that will be correlated, even when they're far apart. So here is one thing. If two people are correlated, one could be in Europe, one could be in USA, but they are still entangled. This is interesting, isn't it? That the distance makes no difference. So this is called, any change of one qubit affects the other. This is called teleportation of a state. And that is what we used in quantum key distribution, actually. Einstein called it a paradox, since change seems to happen at a speed faster than light. How can my thought reach somebody in Europe? When I'm thinking negative, they are thinking negative. How can that reach so fast? Or think about something else. And then in 2022, I mean, this was actually wrong. Actually, Einstein has been proven to be wrong on this. But anyway, in 2022, the Physics Nobel Prize was given for the experiments with entangled photons. So the entanglement now is, basically a standard thing, and you can easily create entangled photons in the lab. And that is what we used for communication. As you can see, this is the best thing for the communication. So entanglement allows communication via qubits. So now, how do we do networking? I wish actually if people could ask questions, and if the host could give me the questions, I could answer it. But if not, then I will continue and we'll answer the questions at the end. It's up to the seminar people. But anyway, so how do we quantum networking? So when I started in quantum networking, I made a stack diagram. We are computer networking people. We always like 7 layers. So I put a 7-layer stack of quantum. The bottom layer is physics, where they talk about fiber and waves and whatever. Then the second layer is hardware, which is basically computer engineering. We call it ECE department. And they work on repeaters and things like that. And then comes the systems people. Okay. And we networking people are systems people. We don't do fiber and things like that. We probably use them, and similarly the hardware, etc. But we design protocols. And then there comes the people who apply. So there are people who do software engineering, and they can write applications for computing, networking, cloud computing, and so on. So it turns out, if you read a paper on quantum, 99% of the time it is a physics paper. Okay? That is what makes it very difficult to read and understand, because we are not physics people and we don't really care that much except basics, right? And then maybe some percentage of papers are from people who are electronics people, and they will say, well, how they designed something. And so that is somewhat understandable. And then there are very, very few papers on networking. And that has a positive or negative. Positive that you are first to get there, and just like that ENIAC computer, people who designed ENIAC computer became probably, the best computer scientists. Similarly, if you do now, whatever is happening in networking, you will be the best quantum networking person, right? So that is one. But negative is that whenever you submit a proposal to any funding agency, it is reviewed by physics people. And they say, oh, there is no quantum here. Or, things like that. So there is right now a big divide because systems people are not reviewing the papers and system people are not writing that many papers. So I find that every time, we send something and they say, well, where is the quantum here? All right. So I will show you where the quantum is, but they want to see phase, blah, 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 and other things which we don't do, any of the math. And what we want to do is we really want to design quantum data center and cloud services. I presented this 7-layer diagram to Cisco and they really liked it. So they are funding my research. And their goal is to develop quantum data centers, which they are very good at. Actually, IBM has also basically given the data center job to Cisco. So let me start with the simplest network. And simplest network is just one hop network. A and B want to talk, but they are far away, so there is a repeater in between. So this is not really a network because when we teach networking, we tell people that if you just have two nodes, that is a communication. So this could be called quantum communication rather than network. Network will come in a few slides. So anyway, how does the quantum communication work? So suppose A and B want to get entangled. A will generate a qubit and generate an entangled qubit as well. So basically, it is very easy to do that. You can have any bit and then you just pass through a circuit and you will get an entangled qubit. You can have any qubit and pass through a circuit, you will get entangled qubit, and you can send through the fiber that entangled qubit to repeater. The other node will do the same. They have a qubit called Q4. They will develop a copy, actually entangled copy, and send it to repeater. The repeater will do some kind of observation of these and then tell both A and B that this is what they should do. And once they do that, this is out of the circuit and these two bits Q1 and Q4 are entangled. Basically what this repeater does is it tells them how to really look at these qubits. And so basically it is what they call the basis. So they determine the basis in which to look at these qubits, and they are now entangled. So this is called entanglement swapping. Swapping because basically this is acting as a swap, basically. And so this is swapping the entanglement. And you can do these repeater things for multiple hops. It doesn't have to be one hop. You can put 5 repeaters on the way. Or they don't have to be repeaters. There could be computers who are repeating. So you could have many, many hops. And then so you got first level of networking, which is simply repeating, swapping. So then you need to do little bit more. And so this picture, which is actually based upon a paper which I recommend, is from NIST, which talks about entanglement routing in quantum networks. It shows that basically if Alice and Bob want to talk, first way to do is just do what I just showed you, that they keep a repeater and they get entangled. Second way is this actually has a problem in the sense that every time you repeat or every time you go with the distance, the entanglement becomes basically less and less correlated. So we say that the fidelity has come down. So the entanglement loses the fidelity. So what can you do? Well, you can have two entangled links and then combine them to make a high fidelity entanglement. Okay. So this is purification. So there are several words that I have introduced here. First is memories. These memories hold the quantum bits. Second is the repeaters. Repeaters swap the entanglement. Then I have introduced the word purification, which means that you can increase the fidelity. Fidelity means correlation by having multiple channels. And then classical channel is always required. This is one thing which people don't realize, that quantum communication or networking cannot happen purely in the quantum domain. You need the normal classical channel, at least right now, to give all these signaling which the repeaters or other people want to give to each other. So the signaling goes to this classical channel, which is not quantum. All right. So the all networking right now is hybrid. Hybrid means both quantum and non-quantum. Particularly, if you want to send a lot of data, you will send the data through the non-quantum. The keys might go through the quantum. So what is the problem? Why is it so challenging? There are 6 reasons why it is so challenging. First is entanglement of a link is destroyed once the data is transmitted. So as soon as the receiver reads the data, the link bit is gone. Right? So you have to create new bit and you go through all the process again. So qubit is lost at the sender due to measurement. Even though only the receiver read it, the sender's qubit is also gone. So decoherence, even if nobody reads it, the qubits decohere means they just start decreasing and disappear because temperature is not constant. The temperature could be, not zero, but might be some few little bit up, and so they really lose. So the entanglement can decohere. They stay for a few milliseconds to a few seconds. And so you have to do everything that you want to do within that time. All right. Fourth thing is that when you try to entangle and when you try to swap, that is also probabilistic. Everything in quantum world is probabilistic. So swap may not succeed. So there is a probability that the swap will not succeed. There is a probability that the entanglement will not happen. The probability that you will not get the qubit, and the probability that qubit will be 0 or 1. So this is just whole, mathematics. So correlation among entangled bit is not perfect, and that correlation is called fidelity. So if fidelity is 1, means it is perfectly correlated. If it is 0.9, it is good enough to do the work. But if it is 0.4, it is not good enough to do the work, right? So fidelity can be improved by combining many entangled bits, and that is called purification. And we have a paper. So actually, what I am doing is every time I give a reference, I have how to get it. Everything in this presentation you should be able to get without anything, just by clicking. So if you clicked, on any reference, you should be able to get to that on your browser. And that's why it is important to have the PDF version of this presentation in your hand. That way, you can just keep clicking. You can click here and get the whole presentation, but right now you don't have the PDF. So the routing problem. The simplest routing problem is how does Alice connect to Bob, not in a single link, but in a network. And the simplest network is a grid network. Now, this is how the fibers are connected. And we say, okay, all right, now please start entangling. So some will get entangled and some will not succeed. So let's say this got entangled to that, this got entangled, this got entangled. So all these lines which are left now in this on the right side, they're entangled, and things which are not entangled are now spaces. So this is the topology. Now in this topology, we have to find the shortest path from Alice to Bob. And of course, you do whatever you want to do, Dijkstra or whatever else, and you will say, okay, all right, this looks like the shortest path. And so this will be the repeater, and actually all of these will be repeaters on the way. But basically, the rest of them will be not used. And what will happen is, question is, what do you do with the rest of those entanglements? Do you throw them away or do you keep them? And so that is coming up in the next slide. But basically, this is how the routing is done, is that you entangle, and then you get the topology, which is good only for one coherence time, because as soon as the coherence time, that second is over, all of these will be gone anyway. So within that time, you have to find the topology, you have to find the shortest path, you have to send the bit or whatever, and then, done. Now the next network. So the dynamics is very high. when we were doing wired networking, the dynamics was very slow. But when we started doing wireless, the media changed so fast that we had to find a different kind of coding. We had to find different kind of retransmissions. We had to find different protocol sets for wireless. The whole TCP with wireless, there are hundreds of papers that are still published. The same thing for quantum. It is much more dynamic than wireless. It is basically every millisecond to a second, the network topology has changed because we don't know what the topology would be next second. You cannot do, beforehand, right? So we have to find that. So we did start with this kind of stuff some years ago. And then one thing which we noticed was that most of the previous work assumed that the time is slotted. So they will say, okay, we will try to entangle in the first slot, and if it doesn't, and then maybe find the route in the second or something like that. But if it doesn't succeed, then everything is lost and then we start all over again. So there are several problems with that synchronous approach in the sense that several entanglements are lost for nothing. Third thing is that if the coherence times increases, the entanglement could last for 5 slots, but we cannot use it because it is gone in the one slot, basically. We have to recreate something else in the next slot. So we started with asynchronous. So we proposed an asynchronous entanglement routing, and there is a paper on that, and as you can see, the URL. And with that, basically, all the unused entanglements can be used until they decohere. Okay. So basically, we showed that really improves the performance significantly. And just to show you some graphs here. So these, just like everybody else shows, we are showing that we are better than the world, is that this is the entanglement rate, and the bottom graph is synchronous. The last graph is synchronous, this dotted line. Actually, this line maybe, okay? Synchronous. And then if you have the coherence time of 1, you are less one slot, right? Then you are less than synchronous. But if you have 2, you can become much better than synchronous. 3, much better, and infinity, very good. So as this coherence time increases, which it will with the improvement in the technology, we are moving in this direction, and therefore we have to leave synchronous and get into asynchronous. Now everything is a probability. So this on the x-axis here, what I have is a distance, and this is the entanglement generation rate. In the second graph, I have on the x-axis the probability of generation, P, and the generation rate. In both cases, the synchronous is lower and ours is better, which is what you would have expected anyway. Otherwise, why would somebody publish our paper? So anyway, so that is just an example. I really don't want to sell our research here because you can read all of it on my website. And then basically Cisco came back and said, no, actually the grid network is not very interesting. Can you do some real networks like SurfNet, ESNet, Internet too? So we analyzed those, and all those results are published now, and you can read all about it. So it works there too as well. I mean, the technology. There is one more thing I forgot to say, that our routing technique was very simple. Actually, we did not use Dijkstra or anything else because we felt that there's not enough time to do all that. So we used something very simple like RPL, which is used in IoT, or in Ethernet spanning tree to find the spanning tree. That is kind of thing. DODAG is the destination-oriented acyclic graph. The destination-oriented directional acyclic graph, right? So DODAGs, so we show that if you just represent it as a DODAG, then basically you can quickly find the route to the destination. I would not go into that detail right now because this lecture is not really meant to sell our research. Here I just want to motivate you that this is the kind of things that happen and you may need to do. After that, basically the problem changed. The problem is really before it can go to that surf net or whatever, we need to basically do quantum inside the data centers. So we started working in the data centers. Now in the data centers, just like currently there are many racks, each rack has many quantum computers and they have to be connected to each other. So that is the problem, is that how do you connect? First of all, how do you connect? That's the real problem because there are many ways to connect racks. And the second thing is, what is the best way to do the jobs? Now, there are many users, many jobs. What is the best way to allocate resources so that it is fair and efficient? So there are lots of problems in quantum data centers. And so that's the whole field which is all ready for you to work on if you ever got into this thing. And it's not just the data center. It turns out that even inside a quantum computer, you need networking. Why? Because the quantum computers are very noisy. If you have 5 qubits in a quantum computer, they will be very correlated qubits because they have the same temperature, same environment, same everything. They will be very correlated, and you don't want that. So what you do is the error rate is very high, and the error rate varies very super linearly with the number of qubits. That is why it is very difficult to make quantum computers with large qubits. Now they have made some quantum computers with 500 qubits, like Google has done, or IBM has done several thousand qubits, and there are others who claim 100,000 bits, but they are not really realistic yet. So the idea is, what happens is, as you increase the number of qubits, the noise increases, and then it becomes unusable. So the best way to make a big quantum computer is to have small computers and network them. So that is called a cluster. So the cluster of quantum processing units is what we need. Cluster of quantum processing units. Each QPU is very small, but they're connected by a network. And so that network is somewhat similar to what we saw in the data center, except that the range is very small. Instead of going meters on the fiber, we go only centimeters. High fidelity, and the fidelity is very high. Clocking, etc., is all very shared. So some of these things make it easier. Some of these things, basically most of these things make it easier actually. And there are no repeaters. Basically, the QPU to QPU directly you can create entanglements. But what we do after that is that then you use qubits from different computers and you can do error correction on them. So that way, that is what people are thinking, at least, or some people are thinking, that the best way to develop a super quantum computer is to use a whole bunch of small quantum computers in a network inside the chip. So the chip itself has all of these computers, and it becomes a supercomputer. Now, routing algorithm could be anything. Generally, we use shortest path, but you could also use shortest k path. So instead of one path, you find 2 paths. For example, in the networks that we had, grid networks, for example, in the grid networks that we had, we could have found one path and we could have found another path just in case this one doesn't succeed or something happens, then we go through the other path. So that's why you would have k paths rather than one path for fault tolerance and purification. Second thing is many users, multi-users. So most of the time we assume only one user, but that is not realistic. Each computer and each data center is used by many people. So we have to worry about the fairness. It is multi-link, and we showed only one link between 2 computers. No, actually, you can have multi-links. Even if you have only one fiber, you can have 5 quantum links in that fiber. So multiple links and then multicast. And you don't have to just go one direction. You can go multiple direction. I will show you more on that in the next slide. And then probabilistic nature of the entanglements makes several variations mentioned in the literature as static, proactive, unrealistic. So I have read lots of papers on quantum routing, and they say, well, we can do static routing. How do you do static routing? There is nothing static in the quantum world. Everything changes every millisecond. So static is just a dream. Similarly, proactive. We will have the circuit or everything beforehand. How do you do that? You just keep all possible combinations in a memory with hundreds of computers in the data center. It's very unrealistic. So really, it has to be done on the spot. And of course, there are several ways to optimize that. Now, I wanted to talk about multicast. So how is multicast possible? So I told you about a repeater that can talk to two computers, right? But it is possible to design a repeater which can talk to three computers at the same time. And it is possible to have 3 bits, 1, 2, and 3, which are entangled. It's not just 2 bits entangled. You can have 3 bits entangled, and you can have 4 bits entangled. Now, this is not done so far very much, but GHZ, those 3 scientists have introduced this, and this allows quantum multicasting. So with that, your network will become like this, and everything that is sent from here will reach both B and C. So if you want to share the key with many people in the group, you can do that in quantum. So other people have used machine learning. Machine learning basically is being used everywhere. And if you write a proposal today, if you don't have machine learning, then people feel that you're not up to date. So just put some machine learning there. I've seen lots of proposals which I have reviewed myself or others. They have reinforcement learning, deep reinforcement learning, and graph neural networks, GNNs. These are the 3 popular techniques to somehow find the routes. And maybe they will work, maybe they will not work. But this is something to try right now, and it is something that will get you some money. The other problem that we ran into is in the data centers, because the number of links, as I said, each link could be multi-link, and then each job could be, there could be multiple jobs in the data center. So let's say there is a job which wants to go from A to B, and there's another job which wants to go from C to D. Now, both of them need this link. Now, if there are 2 links, of course, both are happy. I can give one to green, one to this one. And if there is only one link which is materializes, whom should I give it? Right? So that creates a resource allocation problem. This is another name for congestion control problem. But if I say congestion control, people say, hey, wait a minute. In quantum networks, where is congestion? Well, this is congestion. When 2 people try to get the same thing and only one can get, the other is lost. Basically, that is what the congestion is all about. But so I don't use the word congestion control. I say resource management. Basically, this is the resource management issue, is that you have limited resources and there are more users. So how do you allocate these resources? There is a whole set of papers on that. We also have one paper we wrote on effective scheduling on quantum data centers. So that's so much on standards activity. Sorry, on the how to do networking. Now I'm coming to standards activity. Just wanted to keep track of time. How much time I have, Alicia? Anyone?
Yeah, sorry.
Let's say 5 more
Yeah,
minutes
go
or
ahead,
3
please.
minutes.
Yeah.
Huh? Alessia.
Yes, please go. We need to finish
minutes?
in 25 minutes. So we'll have about 10-15 minutes of question and answer. So you still have maybe 5 minutes.
Okay, all right.
Yeah.
So I will go through this
Thank
quickly
you.
because it doesn't really make much difference.
Thank
Standards
you.
activities, basically all the standards activities that is happening right now is on QKD. What is QKD? It's the quantum key distribution. So the quantum is being used for exchanging the keys. and the data doesn't go through the quantum, data goes through the regular channel. And so the quantum key exchange is current. There are tons of companies that make equipment for this, and there are tons of companies that use it. And ITU has been standardizing this QKD. So if you look at the ITU standards, there are all these standards on QKD, 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 everything is on QKD. And these are the links. Actually, these are not just the numbers. If you click on those numbers, these are the links, and they will just get you to where you can download them if you haven't not done already. And ITU has done quite a bit of work since 2019. HC has similar work, all on QKD. However, I didn't have to give individual URL because they're all available on one page, which is at the bottom. IETF is doing again on QKD. Actually, they're not doing on QKD. Sorry. IETF is a little bit behind. They are just doing post-quantum. So they are doing post-quantum, which is not really quantum, but if you're interested in post-quantum, you can pick up few IETF drafts, which are becoming RFCs. But they're all about post-quantum, nothing about quantum. So IETF is kind of behind. GSMA, which is the GSM Association, they also have something on QKD. So with that, I just wanted to say one thing, which is the challenges. So the challenges in quantum networking is that the quantum devices are noisy, which I already said that. The error correction is very difficult. Error correction requires many physical qubits to produce each error-corrected logical qubit. So everybody is advertising big numbers like, QuantWare says 10,000 qubits and EQRS says 3,000. But I think these are more marketing numbers than real numbers, because if they were so real, Google will buy them in a jiffy. Okay. So anyway, that is my personal opinion. Now, there are many different qubit technologies. That's another problem. That whenever you do something, and you say, well, I assume that the coherence time is 1 millisecond. Then they say, no, mine is 1 second. So there are 6, 7 different technologies, and there is no standardization. This is like very early days of personal computing. There were tons of computers, so you could not really write anything standard. Then more qubits in a single QPU result in high error rates. So that's a problem. Superposition. Now, I think, hold on. Yeah, those are the challenges. And then common myths. The myths are that the superposition allows quantum particles to be in two places at once. No. Actually, the quantum particle is not in two places. It is in two positions, basically two states, but that is like a flipped coin. It is not in two places. It is just in two states. Head or tail, we don't know which one. Entanglement allows communication faster than the speed of light. This is what the Einstein thought, but that is not true, because the entanglement data cannot be made any sense until the whole information comes through, signal comes through the classical network, which travels at the speed of light. So you cannot do anything faster than the light, even with quantum. Third myth is that the quantum mechanics is only about tiny particles. No. Quantum, there is a lot of quantum applications that we have already been using, like MRI, which many of us have gone through, is basically MRI is quantum. Okay, so there are other applications of quantum. And fourth myth is that the quantum is secure. Well, quantum is not secure. Okay, that is one thing. We wrote a paper recently, last year, that showed that the quantum can be attacked. Okay, so the quantum is not secure. The quantum is considered secure because it can remove this insecurity of the current networks. Okay, but that doesn't mean that that itself is secure. It's like, bandit can also be robbed, right? So that is the security here. That brings me to the end of my talk. And the 4 key summaries is, and this was the main reason for the talk, is that it is best to research, learn, or work in a field at the slight left of its hype cycle. And so this is a prime time for computer scientists to get into quantum networking. Quantum computing is here. IBM, Microsoft, Google, all have invested in quantum computing. Numerous companies are producing quantum-related products and using quantum techniques. So it is here. It's no longer a dream only. While much work has been done on the physics of quantum, system level issues are still ready for research. So more people from the networking community come into this field, better it will be. Quantum networking, resource management, error correction, whatever you work on, including security, they're all open fields. Standardization efforts have been focusing on QKD, but I'm sure as these networks become more mature, the ITU probably will be working on networking rather than just QKD. That's the end of the talk, really. Then I have my publications again, and I have a list of papers that I recommend. Okay. With that, I move on to the last slide, which has a QR code. So if you're sitting in front of a monitor, just scan this with your phone, this QR code, and you will get this slide on your phone right away. Okay. If you cannot scan it, just take a picture of this and scan that picture later, or you can just write down this on paper, or you can just write down rajjan.com on your computer. It will take you to my web page where you look for the talks and look for the ITU talk. You will get that. So with that, I am done.
Thanks a lot, Raj. Very nice introductory talk, and also it's some nice ideas from your research group. I enjoyed it, and I hope it will also give a motivation to our attendees. We had like around 35 to 40 people, to my knowledge. And there is one question that I would like to read to you, and then I have some questions, and then Alessia will take over and ask you some life lesson questions. So Carlos Martinez asked the question. You said that two people can be entangled as an analogy to explain superposition and entanglement. Do you think in the future society could create anti-decoherence quantum computing as a path towards a more humane generative AI? I hope the question is clear. Yeah.
A path towards more human generated AI.
Generative AI. Generative AI.
So so what you are saying is because we can use our human entanglement for communication, maybe we can have human generated. So that whole thing about that example of human entanglement, that was just for fun. Okay. I wasn't really serious about that because I find that is the easiest to understand, and it happens all the time to me, and I'm sure to other people that I call my wife and say, oh, I was thinking about this and that same thing. So we are both worrying about the same problem, same issues, or similar thing. So I don't know whether that is real or not. And if that was real, then of course we could just use that as a communication, and then we could do generative AI and everything else. So basically that, I don't have a scientific answer to that.
I have some questions, and as we wait for the others to ask questions. So you mentioned also right in the beginning, you put there the 1994 idea from Shor about quantum computing. And I remember in the 90s, we used to hear quantum computing is up and coming, up and coming. It took many decades, and now it looks like the quantum computing is at peak hype right now. So I have to admit that in the cryptography, quantum technology is super used. So there are many very major contributions in the cryptography area. But in the quantum computing, we are still slow, in my opinion, although you said that's in peak hype. And then again, networking communications, people jumped on it as usual. You also mentioned in your talk. So it's like it's hot topic now, and so they try to find funding. So some of them they create, especially in wireless domain, some artificial problems just to write quantum and AI papers. So what do you think that in the wired domain, you also focus more on that, like these data centers and also your algorithms for routing. But for wireless, do you think that it will come soon? What is your time estimate? Like, for example, can you imagine a mobile quantum phone and also the wireless quantum channels? So there are many issues. So what I hope it will not die down, like it will become mostly for wired systems or core networks. So what is your opinion about that?
Okay, so let me summarize this question. Basically,
Yeah, I
you see,
talk too much.
sometimes
Sorry.
people jump on a technology which is very much down on the left side of the hype graph, and then it doesn't show up for several years, which is true. And so you really have to wait till it becomes somewhat practical, and it looks like it will come. And if you wait for it to come, then also you can make some money. But then by the time there's a whole crowd, like right now, AI is very crowded and everybody is working on AI. Even I am working on AI because you can't do anything without AI. But what I'm saying is that this kind of hype I have seen on every technology. When it was internet, when internet came in 90, I was there, and then it was the hype, right? And then came, Wi-Fi and so on and so forth. Now, question is, when will I have quantum in my hand? I think that is quite far away. However, I am from an industry that that I spent 50% of my life in the industry and 50% in the academics. So I like to work on problems which are more practical rather than just theoretical. So I'm working with Cisco, and Cisco is not spending their money on just theoretical problems. They want to use something and they're working on their own network, and they will have a network announced within few years, right? And IBM has already announced their computers. Google has already announced their computers. The computers have been announced, and I have a set of slides which I did not go through today. There are lots of companies which are still using, which are right now using quantum computers. In particular, let me say that the quantum computers are very good for optimization. I did not go through the optimization problem. I did not go through any computation problem actually. But if you want to optimize something which takes 2 raised to n years in classical computing, it will just take n years in quantum computing because n bits will make 2 raised to n bits. You see, positions. So it is used for optimization, and that means that if you want to do a drug design, you can optimize, find the right drug design for the right diseases, this and that. A lot of that is being used right now. Okay. And same thing for if you are a telecom carrier and if you have a very big network and you want to find the optimal path, maybe you can use a quantum computer to do that. So the thing is, if the problem is very extreme, quantum computers are being used. Right. And so it is not like now it is a dream far away. However, there is one thing which all new technologies face, and that is that when the new technologies come and they try to uproot the old technologies, the old technology also evolves. Okay, and they will evolve to the point so that the new technology can fail sometimes and can sometimes continue. Okay, we saw that happen with ATM networks. Okay, ATM networks were supposed to, be the carrier network for the future. And once they became ready, IP came around and said, hey, we can do the same thing. And MPLS came in and ATM went away. So that can happen to quantum too.
Yeah. So I hope I was not misunderstood. I did not say that the progress is not there for quantum computers. Yes, I agree. There are fantastic progress in quantum computers part. But the problem is for the future, like wireless devices are getting smaller and smaller. And will we be able to produce these quantum-based machines or handheld phones or kind of like smaller devices and create this pure quantum communication? Or you just said also in your talk maybe hybrid communication, like legacy classical communication with quantum communication solutions. So here's another question that will follow up. So like the focus is mostly the last 35 years is about building one giant computer or computers, like as data centers, as you mentioned, which is one path. Another path could be, can we produce or manufacture smaller computers and connect them through a network, right? Which is better? The first has, in my opinion, tough engineering problems. That's why they are still struggling, right, since 3 decades. And the second one, which will put the smaller quantum computers together, create a network, may have so-called physics problems, right? And what do you think about which path is better? So,
Yeah.
what is your opinion? Yeah.
So this is one thing, is that basically quantum computers are right now very expensive. Okay, right now multi-million dollars for that little
Yes.
box I showed you on the picture. And so nobody can afford it. I can't afford it, and I can't see that how quickly it will come. Until it becomes like 100 or 200 or sub $1,000, nobody will buy in a handheld quantum computer. Now, most of the computing technology actually started big. I did my PhD work using DEC 10, which was a whole room computer, just like that ENIAC. It was a whole room computer, right? And in my master's, I used IBM 360, which was a whole hall computer, a big computer in a whole hall, right? And then it became 11780, like you mentioned, VAXes. And then, it became a PC, and now, laptops, and then it became a phone. That I think is probably the normal way I would see will happen with quantum too. First, let's get some big money things to be solved, and then we can start miniaturizing it, and hopefully by then the technology will be so mature that everything can be done inside a phone. So I think it will not start from the phone and go to data center. It will go from data center to the phone.
Yeah, so actually Chen Hu mentioned that he says to my comment about phone with quantum communication, what point it makes sense to have phone like this. As far as I'm aware of, quantum communication relies on photons, which means light. We wouldn't be able to communicate if anyone just blocked the light source or covered the light receiver. So my answer to him, because it's more to me, is you should not only see from the phone technology perspective, right? You can also have laptops, and as you may know, that light communication is being used now. There are many research going on, even in the underwater as well as in terrestrial cases. Moreover, for the cell phones, which will be based on photons or whatever you said that here, there will be some ways of trying to overcome that problem of called like
Yeah, no, actually, if I can interrupt here,
sure.
I said that the quantum comes from photon. No, actually, it turns out that there are people who are using radio quantum. So they are using radio waves for quantum. So
No,
everything that you do in
Raj,
wireless can be done in a
yeah,
quantum way, because all the waves
yes,
basically at some point basically will have the same thing. If you pass them through two slits,
yeah,
they will show up as particles on the other side. So those experiments, they are easily understood by light, but they apply to all the radio waves. So I would not be surprised if someday the phones communicated with the tower using radio quantum or whatever that is, right? So
right.
yeah, there is a version of quantum which uses radio waves. That's what I want to say.
Actually, it was a comment by Chen Hu, so you didn't say that. So I was trying to answer him. Now you answered it on my behalf. Exactly. In the future, there will be some way of that quantum communication will take place in mobile communications also. So that's, we both answered them. So I don't know, Alessia, can I have one more question, or shall we go to you?
Yeah, if the answer is very short, yes, because we are running
Uh,
out of time.
So also, Raj, I like always your talks, by the way. So you mentioned about your 7-layer, this TCP/IP protocol stack. It looks like your quantum internet. Of course, I'm not talking about the detailed internal organs or protocols of your 7-layer. So it will look like classical internet, like modular and spread out. What you say. So, but then there is also, I also advocate that, by the way. So we need to get rid of that total layers. And that's a long discussion. So, but here's my question. Based on your 7-layer idea, like, classical internet idea, will the physics of entanglement actually allow that, or does it force us into a more centralized design with key hubs, for example?
So actually, these are different problems. Actually, let me just go back to that slide. 1 minute. Let me just go back to that slide. And so you say entanglement is not everywhere. Entanglement is right here in this one layer. Now QKD is an application, data center is an application, this encryption is an application, quantum native cryptography, quantum AI, blockchain, these are all different things.
Yes, of course. Yeah.
And same thing for quantum security and quantum management. These are all different things. And so all I wanted to say was that physics people originally thought that they don't need to worry about the system issues, because once they have the bit and they can just do ECC and just go through TCP/IP and go through. TCP/IP will not work on quantum. So that's what I'm saying, is that basically we need to find quantum way of doing networking and then work also on security and management. But these are not just based upon entanglement, but we have to make sure that whatever security attacks are there on the entanglement or on the entangled channel or whatever are analyzed. Does it answer your question?
Yeah, so this is a long discussion, by the way,
Yeah,
layered
long
versus
discussion.
non-layered, but it's a good approach what you have here, like following the classical way of doing communication, and then we can see what will happen, right? But the point is the following. You mentioned also, I like that, and Alessia, I'm sure you're now waiting for us, but we also need to teach younger people. As you said, you're not writing papers just for writing. Unfortunately, this became a common practice now. People don't care about the practical side. So I hope that the new generation of younger people will really start to progress this field, this area, and write papers that will help advance the technology, right? So that they say, I have 50 transactions papers, I'm fine, I'm very happy. We did that, by the way, too, but now it's really time to have progress the technology, help them, right? Again, thanks a lot, Raj, and I let Alessia take over and then ask you some personal questions. Thanks a lot, Raj, really. Thank you. Bye.
Yeah, thank you.
Thank you so
Ian.
much, Ian, for moderating the session. Thank you very much for your excellent presentation. Very interesting topics. We would love to stay longer online and further discuss. Let's move to the Wisdom Corner now. Which is, well, a unique and special angle to this series of webinars. We would like to add a personal touch. So I will start with my first question. What key advice would you give to young professionals aspiring to build a career in academia and research? In your experience, what essential skills and qualities contribute most to success in these fields?
Okay, so first of all, you cannot say that I want to do research in this and that, because that is what you think today. Tomorrow you will be working on very different things. So really you have to have the skills rather than the technology. You cannot be an expert in AI, let us say, or even quantum for that matter, because quantum will stay, AI will stay for some years and then will be gone. So one thing I just wanted to, I get lots of emails from people who I just did my master's in IoT and I want to do my life in IoT. Okay, well, IoT is too short. Basically, it will be gone in next year. So the thing is, same thing for AI. Basically, people what they do is they follow like we call it herd, and if wherever the herd is going, they just follow the herd. That actually will not make you anything special. That is usually part of the herd. If you really want to lead the herd, you have to think about leading things, which means that you have to think about things before they happen. And so this is where actually I have never never stayed in one field for more than 10 years or 5 years or 3 years, because it just gets boring to me in person, but also some people enjoy that because then now you're the world expert on congestion control, for example. I could have stayed in congestion control. I was world expert in congestion control back in 80s and 90s, right? But now I am not, because there are other things to be solved. So basically, I think this was the first slide. Very important question is to do not basically follow the herd. Do not follow the herd. Basically, you have to see what is required, what the world will need tomorrow, and start in that direction today. Okay. And that's why I always like to see every year this hype cycle thing. And I've been following that for last 20, 30 years and see what is on the left side. Now, this is not true. By the way, this is not the God sent in the sense that the gardener knows everything. No, this is what they have found by talking to a lot of experts and saying that, well, I think, supercomputing is coming. New homomorphic computing is coming. So this is a summary of a lot of experts. And this is the best that is available today. So we look at that and then we say, okay, all right, it may not happen because some things happen here and then they suddenly disappear next year because nobody cares. So yeah, so basically my advice always to all the students is that look for things not because they're just so popular right now. Maybe it will get you the job right now. See, that's one thing, is that if you don't do anything which is right now, then you won't get the job. So I say, okay, all right, do AI, but at the same time, in the background, do something that is coming next. When that comes up, then you do something next, and then while you're still getting a job on that new thing. You see what I mean? So
Yeah, absolutely. Yeah, that's very clear. Yeah.
so that's what it
Thank
is. Yeah.
you. And what first inspired your passion for your field, and how did you turn that interest into a meaningful career?
Yeah, so basically, some of these are situation driven. Let me say one thing. When I wanted to get a PhD, I went to Harvard actually, and I asked the professor what he's interested in. Whatever he was interested in, I worked that one, right? I mean, I didn't have a choice. And then I got a job in digital, and there I joined the networking group. Whatever they're working on, I had to join the networking group. And so, but that is in the beginning. Now I'm in a position where I don't have to join any group. I can just start a group, you see, slowly. So when I was in the beginning, I was the lowest person in that networking group. And slowly I learned from my manager, my super manager, and they were all very expert and very good. And so slowly I became higher and higher thinking. And once I became academics, one thing about the academics is that, and good thing is that they don't have to follow the manager. They can do whatever they want to do, okay, as long as they can get funding. If you get funding, you get a lot of funding, you get a lot of students, you can work a lot of things on those, right? So a academic is one company by himself or herself. So that is one thing, is that in the beginning, if you're just starting out, then it's very little in your control. You have to go to the jobs that are available and slowly learn. But as you grow, try to be in the leading position so that you become a leader sooner than later. And then once you are the leader, then you have to lead the company to success.
Thank you. My last question to you is, among your career achievements, there are many, is there one particular contribution, whether professional or personal, that has had a profound impact on you or also on others, and what makes this accomplishment particularly important, meaningful to you?
So you say sometimes when you try 5 things, 4 things may fail and only one succeeds. And you never know which one will be succeeding, right? So
Yes.
in my case, you said, what is one thing? Now, I always was in the forefront of the technology in the sense that when I started my career in networking, they gave me a problem saying that, okay, so we are designing Ethernet and can you see what would be the problem? And I came up with the answer. I said, no, because Ethernet is very high speed network. It was 10 megabit Ethernet in 1980. It's very high speed network. This will cause congestion. They said, how? I said, yeah, I showed them the experiment that this will cause congestion because if you come at 10 megabits, you can't get out on the roads which are only 155 kilobits. So there will be a lot of congestion and we have to solve that problem. I solved that problem and that is now everywhere in the world. So I take very much pride that, okay, my congestion is everywhere. Schemes are being used. But that is much later, right? And so the thing is, if you say one thing, then I'm very proud of the congestion work. Although, I mean, I still keep trying, doing new things in every field. I believe it or not, after coming to WashU, I was working on wireless and optical. I had the optical company, and then I came here. At that time, I think I was invited by WiMAX forum, so I became 4G guy. I worked on WiMAX. They said we will become 4G. Now this is another story where WiMAX was a way ahead of its time, 4G, but when it became 4G, when it was ready for the field trial, then Qualcomm came back and threw Intel in the back and said, hey, you cannot start this thing. This is my area. And they started something else. Okay. So the LTE actually. So WiMAX went away. So this happens is that you might be doing new things, but then it comes up with a different name. Different names. So LTE came in, which is actually almost WiMAX, but WiMAX went away. Intel lost several $1 billion in that gamble, and Qualcomm was still a lead, which was a lead in 3G, still a lead in 4G, 5G. So this happens in life all the time that the technology may not succeed, or what you are working on may not succeed, but so be it. Not everything you will succeed successful.
Thank you so much. Thanks, Ia, for being back with us for the closing.
Okay, thanks a lot again, Raj. It was very successful. We reached 45 people. Plus, this webinar will be put on YouTube, and we invite people to spread the word, and you can access the whole webinar again. And Raj, very nice, really. We enjoyed it. I mean, I enjoyed it, and also I assume that everybody else enjoyed it. Good to see you again, and wish you all the best. And we will have another speaker, another outstanding speaker soon, right, Alessia?
Yeah, on the 14th of April, Professor Ana Garcia Armada. Yeah.
Yeah, from Madrid, another friend of mine. And I'll be in Iceland, so I'll be joining you from Iceland. So thanks a lot again. Have a nice
Thank you very much again. Thank you.
Bye-bye.
Bye-bye. Thanks.
Thank you.
Thank you.